to see you all. So, as you know, today PI of our consortium and founding member, Professor Bhalchandra Joshi, will be giving a colloquium on Indian pulsar timing array, and it was due a long time because in last June we had a joint means in our data we had that hint of gravitational waves. So that time in many places there were colloquiums and many things. Here also there are seminars at CMI. Here we had TNSF meeting, but that time we got so busy I could not organize anything at IMSC. So it is our pleasure that it is now two purpose. And for IMSC members, you see most of the people are our team member, all these young people. We are total 33 people here. Huh? Yes. So, so we are all waiting to hear from Balchandra BCJ. He is the youngest member of NPTA also because he is the most energetic person. So even if we fall tired, we are not working in the night. He is always working with every group. And he actually did his PhD on pulsars and radio astronomy. Then he was faculty. Then he was postdoc in Manchester. Then for a few decades, he was faculty at NCRA TIFR in Pune. And presently, he is there as Rajaramanna Chair Professor. And he will be talking us about the era of ultra long wavelength gravitational wave astronomy, which has been inaugurated in this last June 2023. So, BCA, to you.
Thanks very much, Manjari, for your kind introduction. And it's always a pleasure to be back to IMSC. I think this is the fourth or fifth time I'm coming here, and especially in this weather, which is generally very, very pleasant. So it's always nice and good to be here. And as Manjari mentioned, I think for people who are not from NPTA, we have the largest ever gathering of our NPTA collaboration here, 32 people as I understand. So it's really speaks volumes about the way Manjari and my other colleagues, Professor Gopakumar, Professor Shantanu Desai, and others, have grown this from merely a three members. This collaboration has now grown to about 44, 45, including our Japanese colleague, Professor Kaitaro, who is there in the audience, and yeah, and his students and so on who have been in this journey with us right from the beginning, all throughout. So, a warm welcome to the Japanese colleagues also. So, I will probably, so I should go up, right? This is, yes. Okay, so I hope I am audible. Yeah. Okay, so thanks very much uh, for providing me this opportunity to be here today. And to my INPTA colleagues, please bear with me and pardon me because you, of course, know everything which I am going to talk about. In fact, you are the people who have generated most of the content which you are going to see here. So this is all the work of our young researchers in this collaboration. So please bear with me if it is a bit boring for you. It's for others that I would be mostly focusing on. So, so to begin with, I'm going to talk about this era of ultra long wavelength gravitational astronomy, which began about 7 months back. Gravitational wave astronomy as such began about 8 years back. So the whole messenger of gravitational waves is not very old, it's fairly recent. So how do I change the slide? Okay. So I'm of course talking on behalf of our collaboration, which is the Indo-Japanese Pulsar Timing Array collaboration, which is a multi-institution collaboration with about 40 members and more from all these institutions which are listed here. And at the outset, I would also like to give a special thanks to our European colleagues in the European Pulsar Timing Array Consortium, which is again a multi-institutional collaboration of 12 institutes, which uses Europe's 5 most sensitive telescopes. And in particular, the Indo-Japanese Pulsar Timing Array collaboration is very grateful to the engineers and the staff of the upgraded GMRT, in particular the telescope operators, who have made possible for us to collect this data over the last 6 to 7 years. Without their help and support, our project would not have been possible. So a special thanks to all of them. Okay, so it's been a long history of gravitation from the first time when Newton proposed his action as distance as the definition of the gravitational force, to the discovery of gravitational waves in 2015, and now the ultra long gravitational waves in 2023. It's been a long journey of almost 3 centuries. And the idea of gravitational waves sort of started taking shape shortly after James Clerk Maxwell in 1864 wrote this landmark paper, The Dynamical Theory of the Electromagnetic Field, in which the paper is mostly about electricity and magnetism and a combination of that to say that what is an electromagnetic radiation. But the last section of this paper, James Clerk Maxwell wondered whether a similar analogy exists for gravitational waves, and do gravitational waves also exist in the same way as the electromagnetic waves. He didn't really do much calculations, but just proposed a speculative idea, which was soon after, in 1893, followed by one of the most brilliant electrical engineers and mathematicians, Oliver Heaviside, okay, whom we know in mathematics for many other things, the Heaviside expansion and so on and so forth. He actually took this idea further and worked out a full paper. Yes. Sorry. So he worked out a full paper in which he tried to carry forward this analogy, and these are some of the expressions from his paper which I have extracted here. And when you look at them, you would find the similarity between the Maxwell's equation very much there in terms of the two curl equations, which are exactly similar to the equations of electromagnetism, which James Clerk Maxwell sort of did that. But in deriving these expressions, he made a very key assumption. And that key assumption was that for gravitational waves to exist, they must have a finite velocity, and that is coded in that expression mu c v square equals to 1, where mu could be changed to sort of define what is the velocity of the propagating gravitational waves. So only if you made an assumption of finite velocity, you would get gravitational waves out of that. And these gravitational waves are actually a manifestation of localization of the gravitational energy, just like Maxwell did localization of the electromagnetic energy. And they would carry energy with a Poynting flux, which is given by the Poynting equation, which is the last equation. Okay. So if you really look at the form of these expressions, they are very analogous to the electromagnetism. And for the details, I refer you to go to the paper on the which is cited there, Electrician 31 to 81. It's a very interesting paper to sort of read there. So this conjecture that the, yeah. Yes, so, yes, you are right. So the magnetic analog of the gravity is the product of the mass density rho and the velocity. So the flux of the mass. That's what brings the first equation there. And that actually leads in the paper, if you go through that, that leads to the assumption that these waves have to propagate at some finite velocity. They cannot have an infinite velocity. So what is interesting about this paper is this was written way before 1905. So well before 1905, Oliver Heaviside mathematically was telling you that there has to be a speed limit in the universe. He had already predated the special theory of relativity before Einstein actually formally proposed it. So it's a very interesting, and if you read Heviside's other papers, it was very insightful papers of Heaviside. And although he's known for few mathematical things, there were many other things which he did. And this was one of those kind of things. So historically, it's very interesting to go through these papers. Now, his point of a finite velocity was taken further by Poincare in 1906, in which actually Poincare almost came up with special theory of relativity, although the credit goes to Einstein. And he introduced the key concept of retarded potentials. And he said that the retardation is a key concept for propagation of gravitational energy in the form of gravitational waves. Yeah. So that was the so that was the early ideas on the gravitational waves. But of course, the credit goes to Einstein for actually having worked out the full mathematics of it. Although in 2016, at the time of proposing the general theory of relativity, Einstein sort of felt that these waves should not exist. In a letter to Schwarzschild, he wrote, "Since then, I have handled Newton's case differently, of course, according to the final theory, that is the theory of general relativity. Thus, there are no gravitational waves analogous to light waves." This probably is also related to the one-sided, exactly the point which you made, that you don't have two different things, and there is no dipole in gravitational things. So Einstein was not able to get over this, that how can you produce waves without having two opposite charges, which the gravitation does not have. Okay. So essentially that was his dilemma, and this was not the end of the dilemma of Einstein. He kept on vacillating over 25 years on, do these exist or do they don't exist? But after this paper, actually the problem which he faced is the typical problem in general theory of relativity, that you have to choose your coordinate systems very well. In a particular coordinate system, you will see no ripples in the space-time. But if you change to another choice of coordinate systems, lo and behold, there are gravitational waves. And when he was struggling here, he was choosing the wrong coordinate systems. And with help from some of other people, he chose the right ones. And then he wrote that my former presentation is not sufficiently transparent, and furthermore is marred by a regrettable error in calculation. That regrettable error in calculation, an admission by Einstein of his mistake, was actually the wrong coordinate systems. And once he sort of fixed that, he wrote a paper 2 years later in 1918 called On Gravitational Waves. A translation of this is available. It's in German, this paper, in which he first proposed all the details of the gravitational waves. And that's the landmark paper for gravitational waves. But the story does not end there. Soon afterwards, he proposed actually 3 types of gravitational waves, including longitudinal gravitational waves, which Eddington showed few years later cannot exist. Okay, and there started a debate between Rosen, Edinburgh, Einstein, and others on again whether these do exist or they don't exist. And in 1936, he actually wrote a paper once again saying that gravitational waves don't exist. So Einstein was thoroughly confused. Although everybody keeps ascribing gravitational waves to Einstein, we should keep in mind historically he never had a very clear idea of whether these waves would exist or not. And that's not surprising given the complexity of the tensor algebra involved in general theory of relativity. The Einstein's equation can only be solved in approximations in certain very, very specific regimes. And that is what creates all the kind of problem, even for Einstein. This whole confusion finally was settled by Bondi, Pirani, and Robinson in another landmark paper in the Royal Society's transaction in 1959, where they, for the first time, unequivocally established the theoretical existence of gravitational waves. And it took another 50 years for the direct detection of these gravitational waves by a terrestrial instrument known as Advanced Laser Interferometer Gravitational Wave Observatory, or Advanced LIGO. And of course, all of you have heard about it. A Nobel Prize has been given on this particular discovery. So it took 320 years for gravitational waves to become a reality from a conjecture, and especially in the last 60 years. And with the discovery in 2016, a new messenger distinct from electromagnetic waves, cosmic rays or neutrinos, which are the other messengers, became available for study of the universe. So what are gravitational waves? Okay. So essentially gravitational waves are waves generated by dynamics of masses, and they are, while analogous to electromagnetic waves, they are different from electromagnetic waves in many ways. First of all, the conservation of mass and linear momentum implies that you cannot have a dipolar moment. So the quantity which is responsible for generation of gravitational waves is the time variation of the quadrupole moment of the masses and not the dipole moment. And if you take the Einstein's equation and in vacuum, you solve them in a linear approximation with small tiny perturbation on the metric. These equations then they reduce into the form of a plane wave equation. So one can show that they reduce to a plane wave equation, and that solution also shows you that these are transverse waves and have two polarizations like the ones which are shown here. And this is because of the quadrupolar nature of the gravitational waves. This quadrupolar nature also means that if you have a circular binary system, that is two stars going around each other gravitationally bound. So if you have a circular binary system like this, it will emit gravitational waves A. B, the frequency of the emitted gravitational wave will be twice the orbital frequency of the binary. So that's a consequence of the quadrupolar nature of the things. So those are the basic features of the gravitational waves. Now, any motion of masses will generate gravitational waves. But for the purpose of this talk, depending on the dynamics of the masses involved, there are four different broad categories of gravitational wave sources that are expected to be discovered. So you have coalescing compact binary systems like the neutron star, or the black hole systems, which can generate short duration and also things like supernova explosion. And both these category of sources can generate short duration, very intense and transient sources. On the other hand, compact binaries can also emit continuous waves over a long period of time, and those are long duration continuous gravitational wave source. A collection of many such continuous gravitational wave sources can form what is known as a stochastic gravitational wave background. And for our purpose, it is this source which is of importance as of now. Now, the gravitational wave spectrum by itself is likely to encompass about 22 orders of magnitude, from attohertz here to few kilohertz here. The 2016 discovery of the gravitational waves happened in the high frequency regime, where the advanced LIGO detected the first gravitational wave source. But the lower frequency gravitational waves are as yet not detected. And the most promising band where you can actually detect the low frequency gravitational waves is the ultra long wavelength or equivalently nanohertz frequency gravitational waves. And this is where the pulsar timing array experiment, which I am going to talk about, operates. Now, how do you actually detect gravitational waves? So for the detection, what the gravitational waves are doing is they are stretching and squeezing the space-time. So to detect this, you need to have a detector which allows you to measure the variation of the proper distance between 2 points. And there are various ways of doing this. The way which succeeded first is to use an interferometer, in which you estimate the shift in fringes as is shown here in this particular animation. So it's an interferometer, and as the arm length changes, you will have constructive and destructive interferences which will lead to a shift in fringes which is proportional to change in the proper distance. Now for advanced LIGO, the arm length is about 4 kilometers. That amounts to the fact that this particular terrestrial detector is sensitive to frequencies of 10 to say 500 or 1 kilohertz, which is the high frequency spectrum of the gravitational waves. And that is what was discovered in 2016 in the black hole coalescence event, which Advanced LIGO discovered. But there is an alternative way of measuring the variation of the proper distance, which is to use the propagation of electromagnetic signals from these beautiful and fantastic celestial clocks called as radio pulsars, which provide an alternative yet a very precise way of measuring the proper distance between 2 points. Now here your detector consists of a pulsar which is several parsecs away. So essentially you are dealing with a galactic scale detector. And since we are talking of a galactic scale detector, you are talking of very long wavelength, or equivalently, you are talking of nanohertz frequency range. That is why PTAs operate at nanohertz frequency range. Also, the other feature is you are talking of frequencies which have periods of the order of a decade, which means to collect the signal, the PTA experiment has to operate over a decade. So by design, PTA experiments are very, very long-term experiments. So you don't get results very, very fast. So since the main component of a pulsar timing array is a radio pulsar, let's look at what a radio pulsar is. A radio pulsars are highly magnetized rotating neutron stars, which are very compact and massive. Okay, they have a mass of about 1.5 times the mass of the sun and a radius of the order of 10 kilometers, a moment of inertia of the order of 10 to the power 45 grams centimeter square. So if you have a millisecond rotating pulsar, you can calculate that its rotational kinetic energy is 10 to the power 45 ergs, which is a huge and immense rotational kinetic energy reservoir. On the other hand, the star loses energy with radiation and particle winds. But this loss is extremely tiny compared to the energy stored in the rotation of the neutron star. It's actually 15 orders of magnitude smaller than the energy stored there. And that means that the pulsar has a very precise rotation and a precise pulse frequency, and hence is the best celestial clock available for doing this kind of an experiment. Okay. Now, amongst these pulsars, so this is the pulsar population, about 3,400 of these pulsars are known as of today. Amongst these pulsars, you have on the lower left corner a cluster of pulsars which have relatively small magnetic fields and relatively shorter periods of the order of milliseconds. And these are known as millisecond pulsars. So these are the pulsars which are the most stable rotators, and they are the best clocks used for detecting gravitational waves. Now, how do we actually sort of try and do that? To do that, you have to time a pulsar. That means you need to find its pulse frequency variations very, very precisely. And you do that by using a technique known as pulsar timing, which is schematically shown here. So in this technique, what you do is that you compare the prediction of a pulse time of arrival, or TOA, which is shown in blue here. So you predict something and compare that with the observed TOA, which is shown in red. And you do this by keeping track of the number of rotations of the star. So if your prediction does not match the observation, the difference, which is known as timing residual, continues to grow with increasing time. And that allows you to do very high precision measurements of various parameters of the pulsar, in specifically the apparent pulse frequencies. And I've given as an example the kind of precision which you can do that. And you do that by doing a simple linear least squares, in which you have a predicted pulse time of arrival, which is your model. And you subtract that from a observed time of arrival, which is your data, and that is what is the timing residuals. And given the measurement error of y error, you sort of minimize the chi-square here, resolving the phase ambiguity by keeping track of the number of rotations of the pulsar. So as long as your model describes the data very well, you will get timing residuals which are white Gaussian. Okay, they are uncorrelated Gaussian kind of time residuals. But if your model does not account for everything which is there in the data, you will see growing systematics. And the examples of such kind of a systematics are here. So for example, if you do not know the position of the pulsar in the sky, you will see an yearly sinusoid as a systematic in the timing residuals. Note the y-axis, which is of the order of about 100 microseconds. So we have such a high precision data here. GMRT data is sitting somewhere here, and the rest of the EPTA data for this pulsar 1909 minus 3744. So this is actual data. And if you do not know the position of if you do not know the motion of the pulsar, you see the same kind of a sinusoid, but which grows with year because the pulsar is moving in position. And many of these pulsars are in binary systems. So if you do not know the binary orbital parameters, x-axis is the phase in the binary orbit and y-axis is the residuals. So you see some kind of a structure there. And last but not the least, if you do not understand the medium between you and the pulsar, the so-called ionized interstellar medium, then again, you will see that there will be a structure with respect to frequency. The x-axis here is frequency and the y-axis is residual. So you can see that there is a structure, and this turnover, this actually can be fitted to a parabola of nu to the power minus 2, which is telling you something about the free electron content in the line of sight to the particular pulsar. So you can make very high precision measurement of all these quantities by pulsar timing technique. And the model which you use, so essentially what you do is you try to predict a time at an inertial frame, which for the purpose of our experiment, we choose as the solar system barycenter. By adjusting your measured observatory time by a large number of factors which are governed by solar system motion, factors which involve interstellar medium, and factors which involve the binary motion, and so on. And all these things will involve a complicated multi-parameter model which will have the rotational parameters, the astrometric parameters, the ISM and the interplanetary medium parameters, the binary Keplerian and post-Keplerian parameters, as well as the dynamical parameters. So it's a fairly complicated timing model. And using that, you make a prediction and compare it with the actual data. And in the process, by doing a least square regression analysis, you are able to extract accurate values of each of these. Any unmodeled effect in this model comes out as a systematic, and it so happens that the gravitational wave, which we don't know its amplitude, will come out as a systematic. So when we are using pulsar for detection of gravitational wave, the variation in the proper distance between 2 points will appear as a systematics in the timing residuals and as a systematic which is a time correlated red noise signal. So that is the signal which we are actually looking for. Now this is easier said and done because there are lots of uncertainties involved in that. The biggest uncertainty which we struggled with for almost a decade from 2010 to 2018 was our own imperfect knowledge of the solar system. So it appeared that we don't know the masses of our planets very well. And this is just an example to show that a very tiny 10 to the power minus 10 times the mass of the sun error in the masses of the outer and inner planets can produce residuals over several years. You know, these are decades. Okay, which are pretty large. The y-axis is microsecond and so on. Now remember that our gravitational wave, which we are trying to look for, also has a period of decades. So if you have systematics which are orders of magnitude larger than the expected gravitational wave amplitude, varying on the same time scale, then this imperfect knowledge of the solar system will mask that signal completely out. So we need to take into account this, and most of last 8 to 10 years have been spent in the pulsar timing array experiments of evolving techniques to take care of these dynamical effects of the solar system. In addition to that, we are faced with other challenges, and the biggest challenge is the so-called achromatic red noise. Now, I have told you that pulsars are phenomenal clocks. They are very clocks with phenomenal stability. Their periods are very stable. While that is certainly true, they do show a small level wander in the rotation rate, and this wander is known as timing noise. And the example is shown here for one of the pulsars, pulsar B0534 plus 2200, also commonly known as scrap pulsar. This is from a GMRT and UT observation of the Kraft pulsar, which me and one of my students did long time back. And you can see that the rotation rate is varying randomly over a time scale which is of the order of few years. Okay, and again, the time scale is similar to the time scale with which the gravitational wave signal is likely to vary. And the order of magnitude of this is about 10 to the power minus 12 to 10 to the power minus 13, somewhat 3 times larger than the expected amplitude of the gravitational wave. So you have a very large noise which you have to contend with, and you need to take it out. In addition to intrinsic effects like achromatic red noise, you also have effects because of propagation delays in the ionized interstellar medium. And there are two different types of delays which are important here. One is a dispersive delay which varies as nu to the power minus 2, nu being the observing radio frequency, that is the radio frequency in which you are observing the pulsar. And that delay manifests like this, that at lower frequency, the pulse is delayed with respect to the higher frequency. Now, if this delay is constant, that is fine. But effectively, the ISM is not constant. It is dynamic. So the ISM drifts across the line of sight towards the pulsar from the Earth. And that drift means that the electron density is changing all the time. And again, it is changing on a time scale which is of the order of few years and decades. So it's a challenge. The other effect which is there is because of multiple path propagation in the ISM. So this pulsar signal gets refracted from different paths and combines at your telescope, which broadens your pulse, which is what is the effect shown here. And this also is an effect which will vary because the inhomogeneities in the ISM vary over a time scale of few years and so on. And that variation is also orders of magnitude larger than the gravitational wave signal which is expected. And this can be seen from our own PTA results. So what is shown here on the plot on the left is a measure of the dispersive delay, which is known as dispersion measure, which is varying at a very small third or fourth decimal place, but nevertheless it varies over a period of time, as you can see these variations here. And similarly, the pulse broadening which I talked about also varies, and this is just a measurement of that variation from the GMRT data. Now these delays vary over months and years, and they have again an log amplitude of the order of minus 12 and 13, which is about 2 to 3 orders of magnitude larger than what we expect for the gravitational waves. So while we are looking for a signal, it's like looking for a needle in a haystack where the noise is much dominant and the signal is very small. So you need to somehow take care of this particular thing, and it's a challenging experiment. Yeah. No, they are observed. So these are all observations. No, so the observations in the PTA are all on radio frequencies because you can actually do non-pulsar observations also. And I didn't put a slide here, but solar wind, for example, can also affect this. So we have just now sent a spacecraft called Aditya L1, which has gone to the Lagrange point, and it will make in situ measurements of the density of the solar wind. So now that is a non-pulsar observation, non-radio observation, and that in situ, it's a density particle observation. So you can actually use that to find out how the particle density is varying, at least towards some line of sights, and fold this in. But the observations which I have shown here, and most of the observations in the PTA experiments are made in radio observing waveband, which is from few hundred megahertz to about few gigahertz. Okay, because the pulsars, the clocks which we are using, they emit in that radio waveband. And these are all measurements. So these are not theoretical curves. Okay, so in principle, if these things were not there and you're, yeah, sure. Yes.
How come you have the small variation? What does that indicate then? Because you should have just an integral change.
Yeah, so there are two things there. So we are looking for gravitational waves, okay, which are non-electromagnetic. They are the effects of the motion of the binary system on the space-time metric itself. So it induces a very tiny perturbation in the background metric, which propagates with the velocity of light. That is what we want to measure. We have no direct detector for doing that. So instead of directly detecting that stretching and squeezing, what we are doing is we are looking at the electromagnetic messenger, which is the radio pulse. So this stretching and squeezing, the variation of the proper distance between 2 points, will lead to an apparent change in the frequency of the pulsar which we are observing. So which we are doing using electromagnetic waves. So it's an indirect measurement, and which is true for LIGO also, because LIGO also is using light, laser light, to do the fringe detection. So, so it's an indirect measurement of the gravitational wave effect. That is what we are measuring. The twice the orbital frequency which I talked is uh, is the frequency of the gravitational wave. Here, when I'm talking of 100 megahertz or 1 gigahertz, I'm talking of the electromagnetic messenger which is used to actually infer that. Now, because the sources which I'll come to, which produce the gravitational waves of interest ourselves, they go around each other in 10 years' time, roughly. Okay. So you will get a gravitational wave. So let's assume it's a continuous gravitational wave monochromatic source. So it's giving you a single frequency. It will give you a sine wave of the order of 10 or 20 years. Okay. So when you look at the changes in the frequency of the pulsar, that will have an imprint of a sine wave of 10 years. Now that will look exactly like this. But this has nothing to do with gravitational wave. This is just the ISM which is changing. So this is noise for us, that is signal for us. This noise is 3 orders of magnitude larger than the signal. So it's a very challenging sort of an experiment, and that's why it's taken such a long time to actually detect the gravitational waves. The essential thing is the value of G. You know, the gravitation is such a weak force that the amplitudes which we are talking about are very, very tiny. And that is what makes gravitational wave astrophysics very, very challenging. So as I just now mentioned, the apparent frequency of the pulsar clock varies due to the perturbation in the metric by a passing gravitational wave, and the expected log amplitude is -15. Compare this with the numbers which I put earlier, -12, -13, and so on. So there is a 3 order of magnitude larger noise than what we expect. So in principle, we can detect this gravitational wave by using a single individual pulsar, because if the pulsar was ideal, everything was ideal, I should be able to measure this very precisely, and I can detect the gravitational wave. But in practice, the red noise in individual pulsar, which is, as I said, rotational rate variations, the achromatic noise, and the chromatic noise, the propagation delays are strong functions of the observing frequency. As I said, nu to the power -2 and nu to the power -4. So those chromatic delays, they have log amplitudes which are much larger than this, which means that I cannot be confident that if I see a variation in a single pulsar, whether that is gravitational wave or it is the noise source. So I need to discriminate between these two scenarios. So individual pulsars cannot be used for detecting the gravitational waves. Although in 1970s, Sazin and Dattweiler, they were the first 2 people to propose using pulsars to actually do this kind of thing. But this kind of a challenge made it difficult to sort of do this. So what do you do that? Instead of using 1 pulsars, you use 2 pulsars. You use 2 pulsars which are separated by a particular distance. Now the gravitational wave will affect the frequency of this pulsar. It will also affect the frequency of this pulsar. So there has to be some correlation in the systematics which you see. The red noise, the chromatic and achromatic red noise for this pulsar will be different from this pulsar. So if I take a correlation, on an average, I will get no correlation of the noise sources, but I will get a correlation of the gravitational waves. So if I can make many, many pairs of pulsars, then I can actually look for this correlation. And this is what was worked out by Hellings and Down in 1983. And this is the expression of that correlation, which looks somewhat like this, where the x-axis is this angular separation between the pulsar pairs, and the y-axis is the expected correlation. And this looks as you see, the correlation does not go to unity. It starts somewhere here and it has a very weird sort of thing. Intuitively, you would like to think it is symmetric. Yeah. So distance does come into picture, but not for the source which we are talking about. And this is what I'll explain in the next slide. So you see this 0.5 kind of thing here that comes because we neglect what is known as pulsar term. So in calculating this correlation, the assumption was that the change in the apparent frequencies of the pulsar is only because of the gravitational wave in the neighborhood of the Earth. Now the pulsar is very far away, so there is some gravitational wave there also. So the signal effectively will be an integral right from here to the pulsar. Okay. But for this purpose, if you neglect the pulsar term, you will get a correlation which is half, and that is why this correlation becomes sort of half here. Also notice that this goes from 0 to 180 degrees and not 0 to 360 degrees, and that is because of the quadrupolar nature of the gravitational waves. And eventually this is not for one individual gravitational wave source. This correlation is an average over a large number of gravitational wave source, which is known as stochastic gravitational wave background, which I'll come to a little bit earlier. So if you keep those considerations in mind, this is how the shape of the curve would actually look like. And this is what all the pulsar timing array experiments would do that. The essential ingredient here is that you will have to use a collection of pulsars which are separated by large angles and which are uniformly distributed across the sky. And an experiment using an ensemble of such pulsars is known as pulsar timing array experiment. So now, what are the sources of gravitational waves? So we have looked at how we detect the gravitational waves, but what are the sources of these nanohertz gravitational waves? The sources come from these monsters known as supermassive black holes. Okay, we know that in the centers of most of the big galaxies resides huge black holes, and this is no longer a theoretical oddity. We have now two experimental results, one in 2019 and one in 2022, using what is known as very large baseline interferometry using a telescope known as EHT, where one has imaged the effect of a black hole on its surrounding in terms of what was called a shadow of the black hole. So one of them is in a nearby galaxy known as M87, and this one is in our own galaxy, the Milky Way galaxy. So we do have very good indirect evidence of existence of black holes at the centers of our galaxy, which have masses of the order of 1,000,000 or billion times the mass of the sun. So they are very massive, supermassive black holes. Now what happens if these galaxies merge? And that is precisely what the galaxy evolution astrophysicists have been working out. What if two galaxies come near each other and then they start merging? So when a galaxy merges, like in this particular case, the friction, the dynamical friction inside the galaxy, which could be because of stars doing exchange operations or the gas itself giving a viscosity or friction in the galaxy, that dynamic friction will drive the central black holes of each of the galaxies together. And at some point of time, they will become gravitationally bound into what is known as supermassive black hole binary systems. And this supermassive black hole binary system will be in existence for millions of years. And while it is sort of evolving, it will evolve by emitting gravitational radiation. And this gravitational radiation will shrink its orbit. So during this particular phase, which is the PTA and the LISA phase here, this supermassive black hole binary system will emit continuous gravitational waves of gradually increasing frequency as its orbital period, its orbit shrinks because of gravitational radiation. So this is a gravitation radiation dominated evolution of the supermassive black hole binary systems. And in the when it is slightly far away, at that point of time, it will fall in the ultra long wavelength band, which I have been talking about, which is the main source for the PTA. The fact that such kind of systems do occur, we have some indirect evidences of it. And this is one such system known as OJ287, which is believed to have two black holes, where one black hole goes around another black hole, and this is the accretion disk of the black hole. Every time it goes through the accretion disk, it produces an electromagnetic flash, which are periodic. And my colleagues and his student, Professor Gopakumar from TIFR, and many of his students, they have been, along with Maury Volkanen and others who discovered this system, have been working on this for last 10 to 15 years to show that this has an exact periodicity with a billion solar mass and a 100 million solar mass black hole sitting in the OJ287 system. Of course, you can explain this system by alternatives, but this is a highly plausible sort of a model. And it's a good example of a supermassive black hole binary candidate systems. So all I'm trying to convince you is that such systems do exist. Now, when they emit gravitational waves, they will, one can show by going through the full calculations that they will emit a gravitational wave which will have an amplitude of somewhat of this number, okay, 10 to the power minus 14 or minus 15 kind of a number. The current PTA sensitivities are not good enough to actually detect this kind of an amplitude. So it's very unlikely that we will detect right now an individual supermassive black hole binary system. None have been detected so far. While we cannot detect a single one, we can certainly detect a cacophony of a large number of supermassive black holes. So it's like almost a harmony orchestra of black holes, which actually is likely to be there because in our universe there are millions and billions of galaxies. Many of them might have merged over the evolution of the universe. Many of them will have supermassive black hole binary systems. They will have different orbital periods, which means they will emit different frequencies. So if you take an incoherent superposition of the continuous gravitational wave from a large number of ensemble or collection of supermassive black hole binary systems, you will get a stochastic gravitational wave background, which I mentioned earlier. And this is what we are likely to get. And we can make an estimate of what is the amplitude and the variation of the amplitude of this gravitational wave as a function of frequency, which is the spectrum of this kind of a stochastic gravitational wave background, which is given by an expression here, where the term which is important is this particular term. Okay, so let me very quickly explain what this term is all about. So imagine a supermassive black hole binary system which has a very large orbital period. Okay, since it's a large orbital period, it will lose less amount of gravitational energy by gravitational radiation. Okay, which means that its orbit will shrink relatively slowly in comparison to a very short orbital period supermassive black hole binary system, which will radiate copiously in gravitational wave energy, which means that its orbit will shrink much faster. So if you look over the cosmic times, you will see large number of large orbital period supermassive black hole binary systems and a much smaller number of short orbital period binary systems. So this is what is referred to as residence time in per orbital period bin or per frequency bin. So large orbital period systems have large residence time. Short orbital periods have short residence time. So that is the dominating term in this expression. And if you take that into account, you get a spectrum which is of this form. This dashed line shows that form. Okay, so that is the form which you will get. Because you have large number density in the large orbital period bin, which is equivalently the lowest frequency bin. So your amplitude is largest in the lowest frequency bin, and your amplitude is smallest at the smallest frequency bin, which gives you this kind of a spectrum, which has a characteristic slope of 2/3. For the gravitational wave amplitude, Hc is the dimensionless strain, that is the ratio of the stretching with respect to the length itself. Okay. Now you can convert this into a timing residual. So when you convert this expression to a timing residual, this alpha you can substitute here will give you a 13/3 dependence. So the timing residual will give you a 13/3 dependence, and the slope of this you should get as 13/3. So this is the main source for the PTA. So if a PTA experiment wants to claim that I have detected the gravitational waves from stochastic gravitational wave background, the PTA experiment has to show two things. First, it has to show a power law spectra which has a 13/3 spectral index. And second, this spectrum or these different frequency bins should have a spatial correlation which is given by Helling-Sen down curve, which I showed earlier. So, yeah.
Here we are talking about 13/3 and amplitude, right? This is estimated from the theoretical models.
Yes.
So are there any error bars associated for this alpha and amplitude from the theory?
I
itself?
will come to that. Okay. When we talk about the tension, I will actually come to that. Yeah. So certainly it depends on the theory. So any uncertainty in the theory will come as an error bar on this. Okay. I'll come to that. But right now, this expression only assumes one thing, that your supermassive black hole binary system is evolving purely under GR regime. That is, it is radiating gravitational waves. That's the only loss mechanism. So the loss of energy from the system is only because of gravitational wave radiation. That's the assumption which goes in giving this. The other possibilities in the evolution, like dynamical friction and so on, or eccentricity further. Again, this is for circular binaries. So the other thing is, this assumes that this is only talking of circular binaries. So eccentricities and all those things are not considered here. Once you do that, you will see, actually they are there in this, as you can see. If you have a viscous disk, for example, you will get this red curve, okay? And if you have eccentricity, you will get a green curve, okay? So this whole band is sort of an error bar. So now that depends on how good you know the supermassive black hole binary evolution, which we don't know. Okay. And so there are several error factors, and later on when we are looking at our results, we will see that those become important. But canonically, if you have only GR dominated evolution, then this should be the spectrum. So this is what PTA experiments are doing for last 20 years. And in this endeavor, there are 4 major regional PTA experiments. The North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, the European Pulsar Timing Array EPTA, the Indo-Japanese Pulsar Timing Array INPTA, and the Parkes Pulsar Timing Array PPTA experiments. They cover time baselines from about 7 years to about 25 years. So they have been in operation for that long. And the sample of pulsars which they actually use ranges from about 30 to about 67. And all these PTA experiments regularly make public releases of their data. And after they have made a public release of their data, they pool their data together in what is known as International Pulsar Timing Array Consortium, or IPTA. And that is the most sensitive data set which is available. And as I said, these experiments are by design decade long, so they have been operating for quite some time. In the last few years, 2 emerging experiments, Meantime Pulsar Timing Array in South Africa and the Chinese Pulsar Timing Array in China, have also sort of joined this kind of an effort. So a few words about INPTA, which I have talked earlier. So many of you, and of course INPTA people, know this very well. So the Indo-Japanese Pulsar Timing Array, or INPTA, is a multi-institutional collaboration of about 40 research scientists, which observes about 29 pulsars, but this is an older slide, 22 pulsars once every 14 days. So it's a regular observing which we have been doing for several years. And it uses the unique niche capability of our facility in India, the upgraded giant meter wave radio telescope. And that unique facility allows us to use GMRT as 2 co-located 75-meter telescopes to make concurrent observations between 300 to 500 and 1260 to 1460 megahertz. This kind of capability is not available in any other radio telescope anywhere in the world. This is very unique to our Indian telescope. And because this is unique, this unique capability allows us to make precision DM measurement and characterize the effect of interstellar medium to a very large precision. In fact, we have, in the history of pulsar astronomy, we have made the highest precision dispersion measurements. We have made a dispersion measurement in many of the pulsars to the 6th decimal place. Okay, and such measurements were not available before our experiment went there, and we still hold the record. Okay, so that is the main sort of uniqueness of our experiment. And the NPTA made its first public data release in 2022, which was led by Pratik, who is sitting here in the audience, and many of the other colleagues in the team who made major contributions. They are all sitting here, okay, except for Krishna Kumar, who is not here. And this comprised of 14 pulsars. And for the first time, we released a high precision DM time series, an example of which is shown here to the rest of the world, providing a very unique data set to the PTA experiments and so on. Now, a word about our European colleagues, the European Pulsar Timing Array. So our European colleagues use 5 of the most sensitive telescopes which are listed here in Europe to make their observations of about 25 pulsars over the last 25 years using frequencies between 1 to 8 gigahertz. And they have sort of made a public data release of this data split into 2 parts. One has the longest time baseline of 25 years called DR2 full, and one has a shorter time baseline of 10 years, which is called as DR2 new. The former long time baseline in DR2 full allows you to measure the model parameters. If you remember, I talked about timing parameters, astrometric, rotational, ISM, dynamical parameters. Those timing parameters have been measured to a large precision using the longer time baseline in the DR2 full. So that was the usefulness of the DR2 full. The DR2 new, on the other hand, was observed using newer instruments and techniques like coherent dispersion. So it has less systematics and much higher sensitivity. And that is why DR2 new is a much more sensitive sort of data set. So this they have made a public release. Now, if you compare the NPTA and the EPTA experiment, one will note that so in NPTA DR1, our time baseline, not written anywhere here, but our time baseline was about 3.5 years. Okay, and our frequency coverage, as I said, is from 300 to 1460 megahertz. European time baseline is 25 years, but they observe from 1 to 8 gigahertz only. So NPTA lacked long time baselines, whereas EPTA lacked lower frequencies. So in that sense, our data and our European colleagues' data was perfectly complementary with each other, and hence the two PTAs decided to do a joint analysis of their data set, and the results which I'll present is from the joint analysis of this particular data set. Okay. Now, of course, the other PTA experiments have been regularly releasing their data, and they did not find gravitational waves till 2020. There was a hint of the spectrum of stochastic gravitational wave background in 2020, but they didn't find any gravitational waves. So in this analysis, what has been done, which is new as compared to earlier, we have used a Bayesian framework to characterize the achromatic red noise, which I talked about earlier, as well as the ISM noise, which I talked about earlier. And as I said, those noise sources are 3 orders of magnitude stronger than the gravitational wave noise. So doing this was certainly useful. And I will not go into the details, but this is how in the spectral domain you actually find out a power spectrum and then generate a Gaussian process. And these are some of the examples from both our and the joint analysis. So this effort was led by Aman Srivastava, who is not here right now with us, of the NPTA data, where what is shown in these plots are the posterior distribution of the achromatic red noise and the chromatic red noise. The chromatic red noise could only come because of our low frequency coverage. And the plot here shows the result of combining our data with the EPTA data. The gray posteriors here indicate the posteriors obtained from the data which was from EPTA alone, no NPTA combination. And the blue posteriors are the ones of the EPTA plus NPTA combined data. As you can see, the blue posteriors are much more constrained compared to the gray posteriors. And that is the power of the NPTA data, which allows you to estimate the level of achromatic red noise and the ISM noise much better than what was possible in the previous analysis. So that's the value which we bring to this entire joint analysis. And once you have done that, you actually sort of interpolate the noise in what is known as Gaussian process realization, and examples of for 2 different pulsars are shown here. So these are fluctuations which have nothing to do with gravitational waves. These are fluctuations entirely because of the noise processes. So in your timing residuals, you will subtract these fluctuations out, and hopefully what would be left would be that 10 to the power minus 15 amplitude gravitational noise. So it's very clear that getting a good noise model is important, because if your noise model is corrupted, so would be your gravitational wave, and your sensitivity to gravitational wave will be very, very poor. So one thing unique about this analysis was that we had much better noise models than in the past, and hence the data was much more sensitive to the gravitational waves. So once this subtraction was done and we ran a full gravitational wave background search, these are the results. So as I mentioned, we needed to detect two things. One is the spectrum of the stochastic gravitational wave background, and the second is the spatial correlation. The plot on the right hand side on the x-axis shows you the spectral index, and on the y-axis shows you the amplitude of the spectrum which is detected. And the contours are the posteriors of our data analysis, with the dashed line showing you the 13/3 slope which is expected for the stochastic gravitational wave background. And as one can see that these posteriors intersect that 13/3, so there is a very high significance detection of the stochastic gravitational wave background. As I said, in some sense, this is not new, because in 2020, a lower significance detection was already there from the PTA experiments. But this is a very, very high significance detection of the stochastic gravitational wave background, which proves beyond doubt that a spectrum which is expected from stochastic gravitational wave background does indeed exist. More importantly, what was not there in 2020 is the plot on the left-hand side, which shows you the Helling and Down spatial correlation. The violins are the posteriors. The x-axis is the angular separation between the pulsar pairs. The violins are the posteriors for each of these pairs. And the solid line is the HD correlation, which I talked about earlier. These show reasonably good match to the order of about 95% confidence, and together both these evidence constitutes a 3.5 sigma detection of the gravitational wave background. Okay, so one can now say that in our in-PTA plus ePTA data set, we have a positive detection of the gravitational wave background, and that was the main thing in the June announcement, which was done about 6-7 months back. Note one thing, that although these posteriors do overlap 13/3, they seem to be slightly offset from the expected value. So there is a mild tension between what we expect the spectrum to be and what is the actual spectral slope, and I will have something to say about it a little bit later. While we were doing our analysis, the other two PTAs, the nanograv and the PPTA, were analyzing their own independent data. So their data is independent of us. They also did an independent analysis, and their results are broadly similar to our results. Again, this is the spectrum this is nanograv spectrum, this is the PPTA spectrum, this is the Helling and Down curve from nanograv, and this is the Helling and Down curve from PPTA. So the results are broadly similar, except that in nanograv, the significance is 4 sigma, ours was 3.5. In PPTA, the significance is about 2 sigma. So other than the difference in the detection significance, the gravitational waves have been independently detected by the other two groups, and all the 4 PTAs together made the announcement on June 29th of this particular results. Okay. Post that result, we actually tried to look for consistency, and that is what is indicated in this plot, where the different colors represent the spectral slope and the amplitude for different PTA experiments, and the black contours refer to the posterior when you just do a quick and simple-minded combination of data from all the PTAs together. So as you can see, all the experiments are sort of consistent with each other, and more interestingly, the black lines are showing narrower posteriors than the other ones, which is hinting to you that if all the PTA experiments combine the data together, we will get a much higher significance, maybe 5, maybe 6 sigma. Okay. However, this result should be treated with caution, because different PTAs employed different noise models. And in some cases, the noise model of one PTA were in tension with the noise model of another PTA. So if you just take data from all PTAs and combine together, that result may or may not hold when you do a full careful systematic combination. So one should treat this result with some sort of care. A lot of work in comparison of these posteriors was done by one of our student members from TIFR, Subhajit Danbat, who is sort of shown here in this particular thing. And these results are under review. They have been submitted as a paper in which many EPTA members, many of the members sitting here, have made a huge contribution in the analysis of this data. Okay, so we have detected gravitational waves. Now, yes. Is there? So our problem, as I said, we had a baseline of only 3.5 years. Okay. So if you go to this, let's say this spectrum. So as your experiment time baseline increases, you start going lower and lower frequency. Okay. So in PTA somewhere here. For us to do an effective analysis, we need to be somewhere here. So 3 years of data was not sufficient for doing an independent analysis. Now we are doing, and I will mention, we are doing a data release too, which is why we are all here right now. So hopefully when we release this in 6 months' time, we will be able to do completely on our own. We don't need then any other data set. And hopefully we will get a 3 sigma detection there. So we have detected gravitational waves. I hope I have convinced you that we have detected gravitational waves. And if we have detected, what are the implications? So first thing is the origin of this gravitational wave background from supermassive black hole binary systems. Okay. As I mentioned, that there is a small amount of tension which you can see in these plots. Okay. The orange plots are the posteriors from the data. So can this tension be explained in terms of uncertainties? The question which Avinash asked, that spectrum, is it a God-given spectrum or you can have uncertainties on that? The answer is yes, because that spectrum is on a certain very simplifying assumptions. In actual practice, the details of the astrophysics are not known. The galaxy formation and evolution models, there are huge amount of uncertainties. We just had a conference, Astronomical Society of India conference last week. And in that conference, there was a talk on the large scale simulations. And the speaker spent about 10 minutes explaining everybody how all their results can be wrong. Okay. So that's the level of uncertainty which we have in galaxy. Let's not get into that, but I'll tell you later on. Okay. So the point is, no, he was right actually. He was very frank and honest. Instead of putting his Romulan and Sigma simulations, pushing for that, advertising for that, he actually brought all simulations together, and he showed that scale effects and so on. There are so many uncertainties that those simulations cannot be believed perfectly. So the details of the physics are very unknown. So what we did was we varied the parameters in the astrophysics, and we found 324K models. So 324,000 models. Okay. Which involved eccentricity, which involved supermassive black hole system and galaxy scaling relations, eccentricities from 0.1 to 0.9 and so on. So we varied all the parameters and formed one model for each parameter. For each of this model, we predicted a spectrum. So we got 324,000 spectrum, right? And we can now make a posterior out of that. And that is the posterior which is shown in green here. Of course, that posterior is perfectly in consonance with the 13/3 spectrum, but it also overlaps the data. And the same thing is shown here, where orange is our actual measurements in each frequency, and the green is actually coming from the simulation of the models. And broadly, you see that there is a very nice sort of consistency there. So this is for EPTA. In EPTA, we believe that the origin looks to be supermassive black hole binary. Another interesting result which comes out here is that if you look for the probability of detection of a individual supermassive black hole binary system, because this individual system has to outshine the background to be able to detect that. So if your background is uncertain, you don't know what is the probability of detecting an individual source. So in this simulation, since we are fixing the background, we can also calculate what is the probability of detecting a single individual background source. And this plot sort of suggests that there is a 50% chance of us detecting a individual background source. And that is the next sort of milestone which the PTA experiments will be looking at. I've gone way out of my time, but I hope it is okay. 5 more minutes. I'll try to wind up as quickly. Nanograph has a very different result. Okay, this is their simulation and this is their data, and you see they don't match. Okay, so the Nanograph's public release says that they have a tension between the supermassive black hole binaries as the origin of the gravitational wave background. But one should see that they used a different code, and their simulation is very simplistic. They didn't use eccentricity. In their simulations, they have only used circular binaries, which I think is not the reality, because in universe, you should have binaries with a distribution of eccentricities. So whether this result one should believe or not is itself, in fact, both our paper and their paper are still on archive. They have still not been accepted. Okay, so I think the referees are fighting from from both sides. I don't know when it will get accepted, but nevertheless, this is the Nanograv sort of result. Also, in our paper, we showed that this tension can simply be explained by a statistical bias, and this we did by simulations. So we considered an idealized PTA, and we injected a 13/3 spectrum, which is this injected thing is at this these solid lines, and then we used our noise models to recover this signal. So the actual noise models which we got from the in-PTA plus ePTA data, we tried to recover. We recover this posterior, which is exactly like the tension which we are getting. Okay, so our claim is that maybe this is a statistical bias. Okay, so I think this we have never covered in any of the in-PTA things. So this is also for all the in-PTA members. If you want, I can give a more detailed thing on that, but these are some of the results which may be new to you. Okay, although we are all authors on that paper, so you guys should know this. Okay, so so obviously we believe that supermassive black hole binaries would be the origin, but as the Nanograv results shows, there is a possibility that there may be backgrounds beyond the supermassive black hole binary. For lack of time, I will not go into that, except saying that you can have the early universe playing as a role for gravitational waves. So for example, in the era of inflation, you can generate inflationary gravitational waves by different types, by tensor perturbation or large-scale scalar fields. They can generate inflationary gravitational waves. You can have cosmic strings. Kaitaro is sitting here. He actually works on some of these things. And there can be other topological defects where the gravitational wave energy can be released as gravitational waves. You can also have ultra light free scalar fields of different mass distributions which can produce gravitational waves, and primordial black holes which can produce that. Many of these can reproduce the data. So if you take any of these scenarios and do a simulation and run it against the data, you will still be able to explain the data on the basis of that. So the PTA data, the take-home message is PTA data right now is not powerful enough to discriminate between these other backgrounds and the background which has an origin in supermassive black hole binaries. So we need to wait for some more time. We need to get a frequency spectrum which is much larger. So we need longer baselines, and lower frequencies in future will help. Okay. And again, so for that we are now combining the data, and we see that there is some combination. So this is ongoing work. In PTA, we have started doing many more things. I will probably not go into the details of this. For lack of time, I will skip. But we are improving our techniques to improve the noise models, especially the ISM noise model, which is the uniqueness of the in-PTA. And this is a work done by Jayakumar Singha and team, which is recently submitted to sort of have a technique to improve this. And similarly, Tomonosuke, who is sitting here, has recently shown that the jitter is actually lower at lower frequency, contrary to popular belief, which means that we can actually employ a much larger sample of pulsars at low frequency to make a low frequency alone PTA, which will allow us to push the significance of the signal much higher up. So these are some of the works. This is almost accepted, this paper. We are discussing today the referee's comment and so on and so forth. So we are doing some work here. And the most important of all, we are gearing up, led by Prerna and Neelam and other team members, including Devabrata, who is probably sitting somewhere here. Yes, there he is, and others. Uh, we are gearing up for the INPTA's second public data release, sometimes in the middle of the year, and this is just an example of that. This will expand, in answer to the question which you had asked earlier, this will expand our time baseline to about 6.5 years and pulsars 29, which probably brings us just within the threshold of doing a 2 to at least 3 sigma kind of a detection completely on our own. So this is ongoing right now, and we hope to sort of make this data publicly released, and then we will run a full gravitational wave background search. And in doing this, we are also generating new techniques. So this is on the INPTA side. In the IPTA, all the PTAs are combining data together, and this is example for one of the pulsars where you can see the richness of the data both in time as well as in the frequency domain. So this will be the most sensitive data set. And again, many of the INPTA members are taking leading roles or contributing in this international analysis. The papers are expected by the end of the year on these particular things. So this is also an ongoing work. And of course, we are now soliciting inputs from various diverse areas of astrophysics to improve our sensitivity on one hand, and on the other hand, to provide feedback to those areas of astrophysics to improve their own models. So this is about that. And maybe since I have run really out of time, so I will stop here by leaving the summary on the screen.
Have time for a few questions.
I have a question about the backgrounds. There must be some irreducible background coming from the fact that, the instantaneous interstellar medium will always be fluctuating, because things are passing in front, the densities are not constant. So there must be some error which is always arising from the fact that these are not constants. The medium is not a constant in which these waves are
You are
moving.
perfectly correct.
And so is there an estimate of how large these are? And
So you are perfectly correct. So the way it corrupts our signal is that it will also be correlated. And it will have a correlation exactly like the gravitational wave background correlation. And in fact, one of the members of the Australian PTA actually wrote a paper on such kind of a correlation. It's very hard to sort of detect this kind of thing and its effect and so on. So that is one aspect. Then there is another aspect that we are looking at one realization of the universe. So if you consider it in a statistical sense, there will be something known as a cosmic variance on that HD curve. So the HD curve which I showed you was just one single curve. Actually, it will have a band of error bar around it, which is the cosmic variance. So we also need to account for that. And there is a philosophical problem in all PTA experiments. Although we are 4 PTAs, so you may think that there are 4 independent experiments, but that is actually not true, because all 4 PTAs are looking at the same pulsars. The detector is not the radio telescope sitting in India or radio telescope sitting in America. The detector is the pulsar. So since you are looking at only one pulsar, effectively you have only one experiment. So I did say consistency, but in some sense it's a false assumption philosophically. So it has some implications in the significance value of this detection. And there is a big debate going on in the international collaboration on how to characterize it, okay, which is still not totally settled. So yes, there is a error bar on those kind of backgrounds, and is something which one has to sort of look at a little bit more carefully.
May I? If there are not many other questions, otherwise I'll wait.
Yes, Gopu, go ahead.
Thank you very much, Balchandra. It's always a pleasure to listen to you again and again. So I have couple of
Listen to me again and again. Right?
now we do that all the time. So Avinash asked this question about theoretical uncertainty in the spectrum, not the HD correlation because of the cosmic variance. Yes, you did, but there is a few things which are not mentioned. It's the same as we use the quadrupolar expression for dE by dF, assuming that everything is happening in the quadrupolar order. So there can be, in principle, uncertainty coming from the higher mode,
Yes.
higher, and of course, you can show that for this kind of experiment, those are negligible. They actually provide an error bar. These are theoretical error bars. I'm not going to talk about cosmic variance here.
Right.
And individual binaries can actually provide you a few other complications. And there are papers which suggest that we don't have the confidence to say that there is suspicious bins. Maybe there's something else going on there which needs further validation and exploration. So that's something, I just want to clarify that there are theoretical uncertainty on that. I mean, it's a purely theoretical. And of course, there are astrophysical uncertainty, which Balchandra talked about, who told you that, the TE by DF is due to gravitational wave emission, can be hydrodynamical, whatever you want. And so that will also turn things around. Again, just want to this is a kind of a comment, we talked about it a lot. People have this idea that we are doing indirect measurement of gravitational waves, and you clarified that, well, that's the way even LIGO works. So the quantification of that statement is that if you think the direct detection of gravitational waves are like electromagnetic observation, which are essentially bolometric detection of electromagnetic photons. So far, we are yet to do bolometric detection of gravitational waves. That's yet to happen. What we do here is obviously amplitude of gravitational waves in software. So that's very different from, when we say direct detection, this is my argument that this is the way it should be thought about. None of the experiments
It's not direct detection at all, because it's certainly you're using some different messenger to detect another messenger. So
that's right. So this is an amplitude measurements which
so
are done in software.
You are not actually making a measurement of the graviton itself. Okay.
Yeah, that's right. It's not a
But-
bolometric.
So it's not a direct detection in that sense, but it's a direct detection as compared to the 1975 or 1919
right.
days
That's
of
right.
Hull-Stellar,
Correct,
because
correct.
there you are not even detecting gravitational waves. You are
Only its effect.
you're only detecting a loss of energy in the Hull-Stellar pulsar because of the shrinkage of the orbit. So that was completely an indirect detection. And the terminology direct detection, I agree with you, is sort of abused a little bit here, because you are actually using another messenger to detect a totally different messenger.
I mean, I think direct or indirect, that's very qualitative. The statement can be, if somebody asks, it's not a bolometric detection of gravitational wave, and none of the gravitational observatories are doing that anyway.
Correct.
And that will never happen. Most probably, this will not happen for the next millennia or something like that. But that's how it is.
Yeah. So given the tools which we have, this is the best which we can do right now.
Right.
And that seems to sort of, and I totally agree that multipoles will be another additional complication in the detection of that. But the estimates, if you look at some of those, so there are a couple of papers interesting which I can send you. The estimates are way below the quadrupolar.
Precisely. Oh, yeah. I mean, that kills by the Newtonian
So
argument.
actually, the cosmic variance, which Bruce and company have been talking about, that will far outweigh the multipolar term.
Precisely. Yes. So that's
Purely theoretically, yes, you should also account for it's like the PN terms which you do in your binary experiment, right? So you should
precisely.
theoretically go to 6, 7, 8 PN, but you don't really go up to that. You ignore most of them. Yeah.
Right. Yeah. I think that's yes. That's the just I want to kind of yeah. And yeah, I think I was taking some notes. And again, I think I just want to ask, I will ask you this: the person who talked about the the galactic evolution models and all those things can't be wrong. Anyway, especially if you're thinking about the JWST observation, that's also going to be problematic.
So this was simulations. So simulations, the problem is that first of all the scale size, because your cell size, you need to reconcile
Megaparsecs,
the
those are
vastness of the
megaparsec.
universe with the galactic scales. And
Right.
if you below 300 parsecs, there are lots of uncertainties. That's the take-home message from those simulations. And there is a variety of simulations which work at large scale. So you have all these big simulations which give you the cosmic web and so on and so forth.
But they're
when,
megaparsec, right? I mean,
but when you try to break down those large scale simulations on the galactic scale to find out what is the merger rate, whether the dynamical friction plays a role before the GR dominated phase or after the GR dominated phase, or even the accretion scenarios, whether the accretion happens on the heavier supermassive black hole or on the lighter or on both of them equally, there are considerable uncertainties. And in my discussion with him, he said ki all these things we don't even consider because our cell size in the simulation does not actually provide for that. And you have your colleague there who does all this, Shivdeep, right? Shivdeep, what's his name?
Yeah. I mean,
Did-
it's not directly, but yes, indirectly interested.
So he actually tries to work below 300 parsec or something like that, I think, or beyond 300 parsecs. So they have also done a little bit of thing, but they have never thought from the galaxy formation side of it. Okay, so if you want some input, we have to poke these simulation guys to provide something which is relevant for our purpose, to see if some of the, say for example, the scaling relations, okay, like Cormandy and Ho and other scaling relations, if we can actually fix it on the basis of these simulations. At the moment, the take-home message which I got from that talk and the discussion later on was nothing can be fixed by them, which
Yes.
is rather disappointing.
No, I think they were more interested to know whether the halo mass and the black hole mass, I mean, that's much more exciting possibility from the PTA perspective and even for the LISA, whether you can fix the so-called observed correlation between, the halo mass and the black hole mass, because that also shows that things are interacting. And why that's sort of interesting is that, it's easier for kind of big simulations to see how the halos are interacting rather than worrying about the black hole. So once you argue that the halos are interacting, that indirectly says that, hopefully the black holes are also interacting because there is a correlation, and you look for the deviation and things like that. This is Avi Loeb and others are now pushing that argument. Again, it's very difficult to, hopefully in 10 years of JWST can do all that. So yeah.
Actually, we what we discussed also was the reverse problem. So here we are trying to come from simulations to the prediction of the background, but you can do the ulta. You start from the background, whatever we have got from the data, and then try to constrain some of these things. And again, it's not some fantastic piece of work, but it's papers. So
Yes.
so it's certainly worth exploring with some of these guys to how to do that. Yeah.
No. So anything low frequency turnover, that will be fantastic. And there may be 10,000 explanation for that.
This reverse problem is true for all of those backgrounds which I talked about.
Yes.
Okay. So if you look at our own EPTA paper, we have already put constraints there.
Correct.
So it's not, so Alberto and others, they have done quite a good piece of work, and there is good constraints there in that paper. I don't know how many. So maybe I should, I see that many people probably are not aware of it here in the NPTA. So we should have a separate colloquium for that, but separate talk for that. But the point is that there are very good constraints on inflationary scenarios and others from our data from that. Not very good constraints,
Yeah.
okay.
Sure.
I would not say very good because our data is not informative. So that is already there. But when you talk to some of these other people, they come up with finer nuances in those models, as all you are a theoretician. So you'll know, a theoretician can think of 10 different stories on the same thing. So another game which can be played is that you start constraining each of those stories, okay, which may or may not make great sense, but nevertheless, it's a paper.
No, so the ideal scenario down the line with a scale will be you see a background, you see an individual event, and those are, those actually will tell you down the line which are the scenarios to be constrained and all that, because you actually see the, the brighter version of this. Like the LIGO, you only see things which are usually, not the galactic size, but, of course, you can say that that's because of the brighter source, more massive sources are more brighter. So, but anyway, yeah. But thank you. Yes, we should worry about those papers. I have not even dared to touch the nanograph, but I have something on the,
I've
yeah.
gone through that.
Oh my
Actually,
God.
see, the point is that at that time we needed to give some interpretation. So all the PTAs have produced some interpretation. But and after that, many people, as Shantanu keeps sending us links, okay, thousands of people have come up with 1,000 other interpretations. Many of them don't probably make sense also, yeah.
One comment, I mean, there is a very clever, there have also been models that
Yes.
without gravity background.
Correct. Yes, purely. Yeah. There is at least 8 to 10. I've never got around to reading any of them, but there are 8 to 10 papers on that topic alone. Okay, so it's a big industry, which is fine, actually, good too. Huh.
Within 3 weeks, we had a Tamil Nadu Science Forum meeting here. So by that time, within 3 weeks, he was saying he had 10 models or something, and they can fit any spectral index, any amplitude, right? So I think now that time he had 10 or 12 models. I think now only one person's group has 1,000 models.
No, so it's good now, 1,000 papers.
Yes.
Okay. So it's actually not bad. Okay, so he can take our data and produce 1,000 papers out of that. He can make a posterior out of that.
But we do not, yeah. Those models which I saw, he told us that time was still within.
That is 1 year back, right?
6 months, yeah.
Yeah, 6 months back. Yeah. Yeah, but it's quite exciting. And the other thing is that as the time baseline grows, so we are right now at 20 years. In another 10 years, we will have gone in the frequency on the lower side of the frequency. That is where interesting things start happening. So the spectrum will flatten, it will turn over. And some of these cosmological models, the flattening and turnover can actually give you discrimination between the supermassive black hole binary versus this. Okay. And so Nihan Pol has long time back written a nice paper in which he had, this was pre-discovery, in which he had explored some of these things. And then subsequent to his paper, there are 3 more papers where people have explored how the lower frequency spectrum will allow you to discriminate between different types of models. So we have to patiently time the pulsars for another 10 to 15 years before we reach that. And then LISA has been approved. So by 2030 or 40, that would be very interesting, because this supermassive black hole binary is continuous gravitational wave in PTA band. But when it reaches LISA, which has a frequency band between the PTA and the terrestrial detector, these binary black holes will merge. So they will produce a intense short duration thing. So if you can do multi-waveband gravitational wave astronomy in 2040s, there'll be wealth of information coming. So yeah, it's certainly exciting in another 20 years time. And I think the main thing is that we have opened something now. So now it's just a question of following it up diligently over the next 2 to 3 decades. So there is, to the in-PTA people, there is quite a lot of bright future ahead for you. As Manjari says, 1,000 papers to ho hi gaya hai, aaram se, from only one group. Okay, so so no issues.
Any more questions? Okay, so if no more, do you have questions?
I was recently at a multi-messenger astronomy event. So they are already looking at LISA. This will give them 3 days to tune LIGO and all the follow-up machinery. So like the double neutron star event, which was the true multi-messenger event, they are saying that if you detect something in LISA, that gives you 3 days to tune everything, make your instruments ready so that It sort of gives you an opportunity for the very first time to know that that an event is going to happen in gravitational waves. So that's going to be the next big thing.
By that
Uh,
time, they
but
will have Einstein telescope also.
yeah, but Mayuresh, that will not happen for neutron stars. That will be only for the black hole, stellar mass black hole
Yes,
binaries,
yes.
which will actually leave LISA and come into LIGO.
Yes.
Up to nearby ones too,
Super
because
noisy.
yeah, neutron stars will take minimum hundreds of years, even if you have something like a fraction of a millihertz, because it's much low mass. Of course, it's highly eccentric or something. You can still think about it, but the usual ones, it will, yes, no, black hole binaries are definitely a possibility, and such system may be the only possibility where the quadrupolar gravitational waves from gravitational wave observation can be constrained better than the pulsar timing. So, because you can predict when they should arrive and all that. So.
Yeah, I have a question. So, if we detect supermassive black hole binaries in the LISA, how well can we predict backwards and find it in the older PTA data? Can that be done?
Yeah, that game can also be played. Okay, so you could say that what was the progenitor of the Lisa event? That's what you
Yeah.
are asking, right? So it could actually be done, but I think the timescales are such that
No,
so
you
I
will
don't
not.
know. Gopu
No,
might know the answer better.
no,
How do you
no,
actually evolve
no. Yeah,
PTA black binary to Lisa?
and
What is the
also
timescale?
that will be thousands or millions of years depending on various properties. So imagine 10 raised to 8 solar mass black hole, which are essentially going to merge within a year in LISA bandwidth or something like that. And if they're sufficiently nearby, that can be interesting in the sense that that will give you a nonlinear memory. And that nonlinear memory, if they're sufficiently powerful, can actually affect our pulsars at some level, which needs to be worked out a bit. But
Correct.
that's very unlikely, other than getting, because the problem is that we are not sensitive to black hole binaries of 10 raised to 8 solar mass. It will be 10 raised to 9. 10 raised to 9 solar mass black hole binaries will merge somewhere in microhertz, which is not at the regime of LISA. So that's the problem there.
You could probably do something on an average, like we do for stars and so on.
Yeah,
But,
memory may
but
be
it's going
one
to be
possibility.
hard. Nevertheless, it's going. Single source would probably be difficult to sort of go back to
Right.
progenitors from.
So you can see in Sarah's cartoon, which Balchandra showed, if you look at that, Balchandra, if you can show that, the way of supermassive, whatever, the lifetime of supermassive, you showed very nice, Sarah's this review, right? So if you, previous one. Yeah, here. You can see that she actually talks about Lisa. You can see that, right? So that, in principle, depending on the masses and all that, she has that's the memory she's talking about. That memory,
So
depending
that
on
the PTA is coming there as the memory
part,
right?
exactly.
Correct.
And the bus will be seen in Lisa. So that's what she's putting all these 3 days and all that. But this will be.
So this is the memory part which Gopu is sort of talking about.
Exactly. But you have to be careful, because some of these things will not be seen. You can see the 30 million years. So that's what I was.
Yeah.
But this is circular, so you can put.
So you have to be very lucky to be somewhere here, and then sort of do this. Okay.
Exactly.
So but one can actually write a paper trying to calculate how many such events are there. There is some initial estimate in Sarah's paper. If you go and look at the Sarah's, in fact, you read the Sarah's full article. I have given the reference here. Multi-band is discussed there. It's not just multi-messenger. Multi-band is discussed in great detail by Sarah in this particular paper. So of course, this was written much before the discovery. So now some calculation can be revised based on that. You can try and figure out that given certain canonical numbers, making some plausible assumption, what is the rate of doing what exactly you want to do that. And it's a nice academic paper.
Yeah. So Avinash, since
Not
you are
possible to verify for 20 years, but but that's okay.
sorry, Avinash. Avinash, since you are interested in TikTok,
Yeah.
TikTok technically, if it's not most likely, but if TikTok merges, it will be seen in LISA. Since there are no LISA,
Yeah.
you are the only option is to look for PTA. I think it's also discussed roughly in a follow-up paper, as you know.
Yeah.
Correct, correct. Thank you.
It's similar, but not here in sports store other things. Now we will be talking about our
Oh, by the way, can I ask, guys, are we meeting at 10:30 p.m. today? I can't hear you, Balchandra.